So next we have Professor Anne Zabludoff from University of Arizona, the Department of Astronomy, and I will let you get started immediately. So
okay, thank you. There's some very similar themes in this talk. That was a fascinating previous talk, and I look forward to speaking with my colleague Future about areas of mutual interest. I deliberately chose this fairly provocative title, but it's amazing that we can even think or even worry about such a world at this point. As you're all familiar with the Turing test, I thought I'd just briefly quote the master, Alan Turing, who proposed the original Turing test, which has become a bit of a moving target. Of course, the original Turing test was, can a human spend 5 minutes speaking to a person and a robot that human could not see and be able to tell the difference? This is the original imitation game, if you read the book or saw the movie. And the prediction was in 1950. And I think most of us can agree that things have gotten to that point, are very, very close. Many humans do treat their AI companions as real people and might be hard pressed to distinguish them from even their best friends. But there's a lot more to what models can do. That moving goalpost of the Turing test moved to some standards proposed actually by the Allen Institute and Peter Clark. Can a AI system pass a standardized US 8th grade science exam? I guess parents of 8th graders might not be impressed by that benchmark, but in fact, that was done some time ago. And more recently, last year, it's been demonstrated that models will now consistently win gold medals and function at the highest level in international math Olympiads. So that again has created questions, aspirations among those, like we just heard, of getting to the point where AI really becomes a companion scientist to us and perhaps ultimately an autonomous scientist that makes Nobel Prize level discoveries. That actually has a name. It's called the Nobel Prize Turing test. It was proposed by Catano multiple times. And it is not crazy anymore to think about a system playing the role of a scientist, hypothesizing, testing those hypotheses, working through the classical scientific method, designing experiments, tweaking those hypotheses, going around again a few times, or tossing them. And one question that was just raised in the previous talk, which is deeply important, is, while we could imagine such a system potentially making lots of discoveries or proposing new ideas, will it have that ability to recognize which ones are the most interesting? So we do have a tendency to view ourselves as intelligent, correctly or not, and to recognize systems that imitate humans as being intelligent. But of course, even Turing recognized that that might be too limited and that the intelligence of AI systems may be very, very different and nevertheless satisfy many conditions for intelligence. So what these digital Aristotles end up looking like, I think, is something obviously people are doing a lot of discussing and potentially raising some concerns about. Nevertheless, we're all embracing our future masters. In astronomy, in my department here at University of Arizona and many other places, we're really recognizing and have been for the past few years the many different applications of different AI methods to different astronomical problems. They're able to handle huge high-dimensional data sets. They can learn physics from sparse and noisy data. They can make fast probabilistic predictions. They can even detect rare or novel unexpected events. In the case of cosmological simulations, neural nets have been shown to be spectacular emulators that save a lot of money and time. And in the case of discovering different types of explosive transients in the universe, just to talk you through these pictures here, we're showing some supernovae, gamma ray bursts, tidal destruction events where stars wander too close to the central black hole in galaxies and get tidally shredded before briefly forming an accretion disk around the black hole. How do you tell the difference when you have a change in the night sky? This is very, very relevant to the legacy survey of space and time that's being conducted at Rubin Observatory, which people here at Moore Lab are deeply involved in. You know, what can you do when you just have a few changes in a photometric light curve to say about the difference between events like these? And because they're fading, you have to be very quick to follow up. And when you have 10 million alerts a night, maybe hundreds of thousands of them real extragalactic sources, and 500 telescopes around the world that could potentially follow them up, you have to do a very big down select. And you need methods to guide you in that sense. Everyone's heard about the miraculous detection of gravitational waves in the last few years. And again, AI methodologies have been applied to denoise those data and detect faint signals at very high sensitivities. And in the exoplanet world, there's a great deal, like many other fields of astronomy, of multimodal data, a lot of different types of data that you'd like to combine to get to be able to interpret the whole of the problem. There are light curves, there's spectra, and multimodal deep learning methods are really being applied now to integrate images from exoplanet transits, spectra, metadata for joint inference to really characterize exoplanets and their atmosphere. So there's a whole lot going on. It's getting better and better as the models are getting better and people are incorporating more sophisticated methodologies. And it's coming for, you know, your favorite science field. We have movies of black hole accretion. There's solar and space weather prediction going on. People are looking at galaxy formation and evolution, autonomously analyzing stellar spectra. So a very exciting time. And it's not just in astronomical fields, it's also in how we actually take the data. So instruments and telescopes are being improved in ways that involve very high precision, high speed, real-time control systems. So for example, work that's being done here, if you actually try to get a very clear image of a star that is affected when you're observing it through the Earth's atmosphere by the turbulence in the atmosphere, it is possible to correct measurements of the wavefront, as you're seeing here, very precisely in a way that dramatically improves your image. And there's also this question of, again, something people both here at Moore Lab and across the street at the University of Arizona and the Department of Astronomy are very interested in, which is, you know, how well we can improve pointing telescopes, and once they're on an object, staying with the object as the Earth rotates. Those seem to be solved problems, and to a large degree, they are, but about 10 to 20% of telescope time, particularly on medium to smaller size telescopes that aren't as well supported, it gets lost around the world due to issues with pointing and tracking. And it is possible through work that's being done across the street and elsewhere to use deep learning, looking at historical pointing data, reading in data constantly from normal operations, updating models during the day to really facilitate better pointing and tracking, and also the alignment of much larger telescopes that have multiple mirrors. And to the right is the LFAST system, which is a new system for which prototypes are being developed, partially supported by Schmidt Sciences, where the idea is to take effectively off-the-shelf small telescope systems and multiplex it thousands of times to create what could ultimately be a 20,000 square meter aperture, and connect all these telescopes through fibers to spectrographs, and relatively on the cheap make a tremendously sensitive machine. But to do that, it's a very complex problem in control. And a lot of the work that Chad Bender across the street is focusing on is trying to get those systems to function efficiently, especially applying AI methods. And I mentioned ways in which AI is helping astronomers, but I think there are a lot of things that are important to astronomers and astrophysicists that if we push hard enough and other scientific domains push hard enough, will actually help AI be better. And they fall into some general categories, some of which I list here. Interpretability is obviously a big one. We publish papers where we have a methods section. We need to be able to explain how we got to an astronomical conclusion. So interpretability of applying models, particularly generative models, is an incredibly important feature. We'd really like to understand how they work, not just to improve them, but to make them believable to our colleagues. Accuracy, enormous. We want models to behave as if they are in the real world and to have some grounding in the laws of physics. Reproducibility. We'd like to know that if you create a model of a gravitational lens system, for example, and the model works on simulations, that it would also work on actual data. Uncertainty quantification is an enormous one, of course. We really want to understand, and using inference models, for example, for cosmology, what the implicit uncertainties are. That's really the business of precision cosmology. And yet, when we don't understand how these models work and they don't predict uncertainties in ways that we can evaluate, it's very difficult to be compelled by the results. Multimodal data, that's very, very common in astronomy to have, for example, as I mentioned earlier, light curves, spectra, other source properties that we somehow like to blend together, including the contextual information, the actual text that's written in paper about what's in the figures, what's in the tables. I mentioned decision-making systems, real-time decision-making systems, very important to astronomers in the way we take our data. We're all very excited about multi-agents. We'd love to be able to incorporate in models in both intuitive reasoning and actual mathematical derivations, ideally to really work on theoretical problems, for example, that were just mentioned. And we have a very open culture in astronomy. So frankly, the computer science community, the commercial industry should be interested in our problems, at least at the level that we make our data, our code available very, very quickly. There's quite a bit of curation. But I think we'll all agree that, for example, generative models are not yet up to the standards of scientific rigor and publication and what they produce. So we ran a bit of a simple experiment here at the University of Arizona last fall, in fall of 2025. I asked students in my graduate course, and they were wonderful sports about this, and they're shown here in the upper right, if they would write a research paper during the term as part of their course grade, but using mostly LLMs. We wanted to see at what level you could make progress on a research problem with which you did not have much familiarity. These students mostly were studying in fields other than galaxies, which was the focus of this graduate class. And they had a range of experiences with large language models, mostly to help them study and check problems. But they hadn't used them in the context of sort of start to finish research project questions. And we kind of talked a lot about it and what their results were throughout the term. But at the end, we came to several conclusions. One was that the error rates were just simply too high. If all they used were large language models, if they did not develop big agentic systems or the types of infrastructure that we were just hearing about, they found a lot of false citations, false links, false paper summaries in fields that they had some familiarity in, and therefore were very suspicious of ones returned, in which they did not. They found that the models made implicit, very oversimplifying assumptions. I know we've all heard that and had that experience. The models were cocky. They often doubled down after being corrected. They had a bit of an attitude. We know that they struggled with generating very complex functional code. That's obviously getting better, but particularly as the code was required to access online packages or APIs to retrieve archival data sets. It just wasn't as simple as writing a prompt, even a detailed one, to try to get at and combine data across many areas of the web. So in the end, only about half of the students thought that this experiment ended up saving them any time. They ended up actually far more suspicious of the models than they had been. And so, ideally, our dream, obviously, if we don't want to be replaced, is to be able to sit down and say, I'd love to make an XY plot. Please go through the entire astronomical literature, anything that's ever been published that's relative to this, put it all together, put on the error bars correctly. Let's play a little bit with the visualization, but give it to me instantly so I can get started on the fun part, which is actually trying to interpret it. And we are far from that. So what are some of the things?
Like 9 minutes.
Okay, then I'll go pretty quickly. Thank you. So some of the issues that arise in the process of actually learning from the literature and grabbing information from the literature when we want to generate a table, when we want to generate a new figure, is obviously that information is not being extracted very well, but there are multiple steps and returned to us very well, but there are multiple steps involved in that. So there's this idea of retrieving the papers, say from the astronomical literature. Some will be missed, some will be irrelevant. How does the model know the difference? The extraction, it can be made much less probabilistic. There are multiple kinds of pipelines that can, and even sort of hierarchical pipelines that can be applied, where if you do things well, as my colleagues in the computer science department do, you can tier up how data are extracted to the point where the more difficult data to extract, more complex data to extract are actually done with more sophisticated but more costly and time-consuming systems, whereas the easier, low-hanging fruit is just grabbed very, very quickly by basic models. There are multiple ways of doing that, and those are the types of things we are implementing, and I'll show you in a moment. But it's still an issue with misinterpretation of text, reading values from axes and points on plots and reading things in tables, and ultimately getting the units to be self-consistent, ultimately getting superscripts and subscripts. Chemists have a terrible problem, nuclear physicists have a terrible problem getting, reactions that don't look right. And then there's this issue of synthesis. Ideally, we want all of these steps. We want searches through the literature to be helpful and return what we need. And the synthesis itself has issues. It often will mix different methods. In this case, if you're asking it for mass of a black hole, there are a lot of different methods: reverberation math, single epoch measurements, dynamical measurements. It doesn't always account for that heterogeneity. It ignores upper limits. It doesn't really understand the context. And the presentation is critical. We want an output as a table. We want an output as an XY plot. We want a database. We want a knowledge graph. And it's very overconfident. There are hallucinations even at that step. So what do we do? And as my colleagues keep telling me, there's no such thing as a free lunch. And as we just heard, people have to be involved. Experts have to be in the loop on these systems, providing feedback. And that feedback has to be cleverly integrated into the problem to set up guardrails, to run experiments, so that we know that the returns can be accurate and they can be complete, because that's what we need to publish a scientific result. So this exploration mining of the scientific literature is an AI grand challenge. It's characterized by the national academies. And what we'd love to have is a simple to use, rapid, accurate search engine. That's a very short sentence, but it's a big ask. And what we've mocked up at this point is, we have a system in place where you can give a request. The system will tune the prompts. It will combine different search tools with large language models, some of which are much more precise at extracting data. It will generate custom programs to solve each search request. It will run experiments to find which the most efficient solutions, least costly, quickest, and most accurate solutions are, and it will cross-validate, verify the results. So I'm going to just show you a brief demo, a very early system that we're trying to get to do this kind of literature search and return of a visualization that would be useful to astronomers. Oh, not sure why it's not operating. Here we go.
DB, a tool for searching for information in scientific papers. Suppose we want to know the halo mass of the Large Magellanic Cloud. Using an existing search engine like Google or ADS will only give a list of papers. However, with AstroDB, we can extract specific facts and answers and get links to the sources. First, let's pre-process a set of 500 PDF papers about the LMC. This pre-processing includes downloading PDFs, converting them to text, and building a search index over their text. Once pre-processing is complete, we can quickly search for any attributes in these 500 papers. For example, let's search for the halo mass. Unlike Google or ADS, AstroDB directly produces a table, with each row containing a value and the source paper it comes from. If the value is cited from another paper, the citation is also provided. Furthermore, each source paper is highlighted, so we can click into the paper and quickly find the context from which the value is extracted. After checking the context, we can confirm that the extracted halo mass of 1.5 times 10 to the 11 solar masses is indeed correct according to this particular paper. Finally, we can provide feedback on the quality of the extraction to help AstroDB improve search results in the future.
Okay, so that was, a mock-up of a very simple system that took quite a bit of talking between domain scientists and computer scientists to put together, but there's so much more we want to be able to do. So here's an example of a new interface that we'd like to implement where you can actually visualize the connections between papers and the histories of citations and immediately link, for example, to the text themselves. But there's so much more. There's so much more that we want to add to the system, including improving its accuracy, improving its completeness, allowing it to work with thousands of users and ingest thousands of papers and return results in seconds. So there are a variety of science test cases. Please feel free to send me your own. We're making a list of things that we'd like to get the system to do, both in terms of the question that you would like to have answered, but also the visualization that you'd like to have arise and be produced by the system. For example, this is the type of system that could gather all measurements of the Hubble constant, the expansion rate of the universe, and put it together in a time history, and really, in this case, reveal or confirm the Hubble tension that cosmologists have been very perplexed by in recent years. We also, thanks to our colleagues like Newt Olson and Monica Sorenstam here at the Moore Lab, really are interested in incorporating this kind of system into the LSST alert stream to improve candidate lists, for example, for fast astrophysical transients, and to see whether or not that can be done much, much more quickly than the many months and in some cases millions of dollars it can take to generate such a filter with pure human use. So one other great.
Some people will need to be at the top of the hour.
Okay. Let me.
Maybe 1 minute.
Okay, sure. So the other thing that I'll end with then is this idea that it's not just exploration and mining of literature that is a grand challenge for science. It's also the automated formulation of general hypotheses. And you could imagine a system like this that I've just described to you being built to generate knowledge graphs from the literature, and then applying causal AI methodologies to visualize the entire logic of the corpus of the literature. So so-and-so claims this, so-and-so shows this, whether it's a plot or in a table, whether it's in text. And there's an inherent logic to the literature, which we as scientists actually develop some worldview of over many years. But we miss stuff and we have our prejudices, of course. But the literature is there with these many different claims, some of which are consistent with one another, some of which would compete and conflict with one another logically. So the ability to visualize that entire logic is really, really useful to us in testing hypotheses, coming up with new hypotheses. So let me just quickly discuss this and then I'll conclude. You can imagine that there are certain drivers of giant planet formation, for example, the host stellar mass and metallicity. And a hypothesis you might have is that it's both the mass and the metallicity that drives giant planet formation. But of course, this causal graph, this hypothesis could go other ways. It could be that the host star's mass drives the host star's metallicity, which then drives giant planet formation. And there are a lot to the right of different directions that those arrows could point in the causal graph, some of which don't make sense physically, but there are multiple hypotheses to consider here. Wouldn't it be great if you could read the text and all the data across the literature and really figure out whether or not stellar mass and metallicity were correlated only when a giant planet were present? That would support the hypothesis on the left. If that weren't true, then any of the possible hypotheses and directionality of the arrows on the right might be in play, and you'd have to go back to the literature or run additional experiments to try to see, for example, whether stellar mass and giant planet formation are correlated unless metallicity is controlled for, which might support the hypothesis, that causal graph as I represented on the right. So the visualization of the literature, through these causal graphs would be incredibly useful because their structure provide a natural explainability. And if you could do this for any scientific problem in which you have some ideas about what drives a particular phenomenon, you could perhaps incorporate all those results at once to try to figure out which are allowed, which are excluded, and potentially reveal new directions, new hypotheses, new causal paths. So we'd like to get to that point and turn that citation graph over to the right into a causal knowledge graph from the literature. And this is something on which we're actively working and seeking collaborators and support, and are very interested as a way of learning from the literature how to generate new hypotheses. So I mentioned that there are lots of ways in which people are envisioning scientific discovery. We heard quite a few in the previous talk, very exciting. There are ideas to put these models into real world robots, let them learn about the world directly. But it's also possible to mix literature and logic, the literature we have, with the logical frameworks we have now, and really try to understand, get a different view of that literature, a much more complete view. I'm going to end there because I know we're out of time, but I'm happy to take questions.
Thank you.
Thank you.
All right, thanks everyone for your patience. We're officially 3 minutes after time, so it's okay if some of you need to leave, but I'd like to still take a few questions for people who can stay a few more minutes. And I see there's at least one hand online. Adele?
Thanks, really nice presentation from both of you, actually. So I was wondering if you can speak on some of the mechanics behind this. So what kind of computing resources do you need to build up these and to test them and then to make them available to multiple users?
Who are you asking this question of?
I can ask to you, please.
Oh, yes. Well, at the current time, they're consistent with resources that we have on campus here at the University of Arizona, but we've entered into a variety of partnerships with other universities, some industry partners, and some national labs, as I'm sure everybody has in the last few years, to make more compute possible. Because ultimately, we do want to scale up, as I said, to thousands of papers, thousands of users, and very, very quick returns. But we're not, viewing that as requiring at this time a special dedicated system.
Thank you.
All right, any other questions? So Knut in the room?
Yeah, so maybe this is a question for both talks. So the fact that an AI can make incremental discoveries now, I guess, I mean, and given the time scale on which it operates compared to human discovery timescales, suggests that if you just let it run, right, it could do great things. But and maybe informed by the kinds of causal graphs that Anne is proposing that we make. But is that vetting process of weeding out things that really are discoveries critical for this, in that if some percentage are just hallucinations or aren't real discoveries, or that would pollute the chain of discovery to the point like where you'd go off into a space where you're not actually making any progress. And what is that sort of pollution, I guess, level?
That's a fantastic question. You can think of that pollution rate, like the percentage of papers that are wrong, using either AI generated literature or human generated literature. So every now and again we find out that something in human literature is wrong, right? The quality rate of human literature is probably pretty high, right? It's definitely in the 90s. I don't know where it is. If you imagine that the quality of the AI, so I gave you a 30% number, right? Imagine it's 50%, then you sort of have compounding errors, right? So the things built on those are going to be 50 squared, right? And then so 25 and then 12, and you don't have to go very far. So right now, in the sort of automated discovery area, everybody I know is working on the same problem. And that problem is automated verification. Because if we can weed out the bad science, then exactly as you said, you just shovel money into it and get results on the other side. So, yeah.
Something, sir. Actually, I do have, sorry. Following on this specifically, I was curious, the knowledge graph concept from the literature, have you already tried to use it or plan? Do you think this is usable to find the papers that are wrong? Basically, would that stand out because nobody else is citing it, or they cite it to say, we cite this because we don't agree?
Yeah, there's so many uses for this, and of course I blazed through it, but you can imagine you end up with nodes, which, for example, are the drivers of turbulence or how galaxies form or giant planets form. And you have these edges that connect those nodes, and then they'll ultimately have a directionality to them based on kind of the preponderance of the claims and the data and the literature. But you can show everything that went into that directionality. So there'll be some opposite claims. Maybe they're not given as much weight because there aren't as many of them. They don't involve as much data. Maybe they weren't cited as much as the others. There are all sorts of ways you could choose to display all that information and have it take you directly to the original sources, which is what this business is about. No scientist is just going to gobble this up and publish on it. You want to actually go back and check, or at least enough that you will start trusting what the model is outputting. So you could imagine those hours of directionality going both ways. Maybe some were a little darker than others based on multiple claims, multiple evidence in one direction versus the other.
Okay. Todd?
Are there any original ideas in astronomy?
Oh, in astronomy?
Or astrophysics?
Who would like to?
Well, you'd have to define what you mean by that. I mean, are you trying to make the difference between something incremental, or are you trying to make the difference between tracing the history of a concept or an idea? Because you could definitely do that with this system. One of the use cases that we frequently, that are frequently suggested to us, and I think a lot of people just have beefs, is, well, no one ever cites my paper, or no one ever cites my favorite paper. And that's where this idea originated. Well, conceptually, you should be able to trace that history using a system like this and see where those original thoughts or original claims may have appeared, and, encourage people to use those original sources.
The reason that I ask that is I have found many times when we have a problem that persists for several years, the answer has often been there in a list of 50
Right.
different possibilities that we could choose. And so, yes, now and then there's something that nobody ever thought of before, but a lot of the really cool ideas, had been there before in various ways. Gunn Peterson had been done years before Gunn.
Right.
Surface brightness fluctuations, which Henry developed brilliantly, had been mentioned, again, decades early, but just a throwaway thing. Nobody developed this, and the reason I ask that is when you say, can these things create original research? I find a lot of what we do is we say, well, Knut picked at this problem, but he really didn't know what he was doing, but I think I can solve it now. With
It's
this.
the story of my career.
Yeah, exactly. But I mean, a lot of what we do, and that's considered original work, can be traced to, ideas that had been around pulled together. The complete synthesis is
Right, it's
very
the synthesis
rare
is,
thing.
is often what will lead someone to make a claim that they're saying something new. Right, and that is potentially a big benefit of these models because.
But I think aiming for that is pretty hard, but you can aim for, talk to your students, say, here, this is a hard problem. People try this in various ways. I think maybe you could do a thesis on this. And so it's putting pieces together that are there, but, it involves original work, but not blinding.
Right, but that student now will spend months going through the literature. If they
Oh,
have a
no,
keyword
I'm
search or
not
even a
criticizing
semantic
that.
search, it's going to come back. Yeah, no, I know you're not criticizing. I'm just saying, where is the time savings here? Obviously, if you have to check everything and it takes you as much time as it did to generate, formally generate these results, you haven't really gained anything. But I think the idea is to really focus on making extraction accurate, being able to return it in structured formats that have been validated. And so that you are more confident of what it is that you are seeing and you can ask for whatever visualization you choose. And that would be an instant starting point. Whereas prior to that, we've spent months developing a worldview and garnering.
No,
these-
I was looking for
Mhm.
what you can do with what you're talking about,
Right.
in the sense that, if you're aiming for the top of Mount Everest, that's gonna be hard, but if you say, hey, here's a bunch of research, what are the unsolved questions
Exactly.
that they talked about, I think that you would be able to do that.
That's right. And you obviously could fold that expert weighting into the system, right? You could choose, and as I said, user feedback is essential. Having domain knowledge put in the system from the beginning is essential. We kept asking our colleagues in developing this system, well, why can't you just return a list of the halo masses of the LMC? And they said, what's a halo mass? And we keep seeing masses. Is it stellar halo mass? Is it total halo mass?
Sure.
That kind of thing, that kind of context models are definitely not there yet to be able to make those decisions. And that's why you constantly, we are important still.
Yeah.
And that has to be, and there are a lot of clever ideas about how to get that, the way you structure that domain knowledge and put it into these systems in a way that makes.
There's a great paper called the diversity innovation paradox that used a neural net to track the appearance of novel concepts.
Oh, I'd love to see that.
And papers, and the conclusions of it are really interesting, but I think that thought is similar to your question.
Okay, so this was super interesting. So if people want to continue, I'm sure both speakers are available to be contacted for a follow-up.
Absolutely.
And then people here, if you want to keep chatting, that's fine. But I suggest that we thank both speakers again for the few of us who lasted so long. Thank you so much. And this was the last Cosmic AI seminar of the semester, but we'll be back the next semester with a fresh new series. Thank you, everyone.